The linear death sentence. Imagine you are a scientist in 1962. You've been handed a top-secret assignment by the CIA as part of Project MK-Ultra. Your task? To find out if a massive dose of LSD can trigger a psychotic break in one of the largest land animals on Earth. You have the subject, a 5-ton Indian elephant named Tusko, the pride of the Lincoln Park Zoo in Oklahoma. You know that a safe, non-lethal dose for a domestic cat is about 0.3 milligrams. Now, looking at Tusko, you do some quick mental math. An elephant is roughly 1,000 times the mass of a cat. So, logically, if you want a similar reaction, you should give him 1,000 times the dose, right? You draw up a syringe with 297 milligrams of pure LSD, the largest single dose ever administered to a living creature. You inject Tusko. Within 5 minutes, the giant trumpets in agony, his legs give way, and he collapses into a massive heap. He suffers through violent seizures for nearly 2 hours before his heart finally stops. The experiment was a catastrophe, and for decades it was cited as proof of the unpredictable danger of psychedelics. But looking back today, the tragedy of Tusko wasn't about the drug itself. It was about a fatal flaw in human logic. The researchers made a mistake that kills businesses, crashes economies, and in this case, killed a beautiful animal. They assumed that life is linear. They assumed that if you double the size of an organism, you simply double its needs. But nature doesn't work that way. Nature has a hidden code, a mathematical rulebook that governs every living thing from the tiniest shrew to the blue whale. And if you don't understand these laws of scaling, you aren't just getting the math wrong. You're missing the secret rhythm of the universe. To understand why Tusko died and why your own heart has a predetermined limit, we have to go back to 1932 and meet a Swiss agricultural scientist named Max Kleiber. Kleiber wasn't looking for universal secrets. He was just trying to figure out how much food a cow needed. He began measuring the metabolic rates of various animals, essentially how much energy their bodies burn while resting. At the time, the scientific consensus was based on something called the surface law. Think about a hot potato. It stays hot for a long time because it has a lot of volume inside, but relatively little surface area for the heat to escape. If you cut that potato into thin fries, they cool down instantly, because they have a massive amount of surface area compared to their weight. In the 19th century, French scientists figured that animals must work the same way. Since animals generate heat inside their bodies but lose it through their skin, a large animal, like an elephant, should have a much lower metabolism per pound than a tiny mouse. If an elephant had the same metabolic intensity as a mouse, it would literally boil its own blood within minutes. It simply wouldn't have enough skin to radiate all that heat away. Based on this surface law, scientists predicted that an animal's metabolic rate should scale with its mass to the power of 2/3. It was a beautiful, elegant geometric theory. There was just one problem. When Max Kleiber actually plotted the data, the numbers didn't fit. Kleiber looked at everything, from a tiny dove weighing a few ounces to a massive steer weighing over 1,000 pounds. He put them on a graph, and what he saw was a perfect straight line. But the slope of that line wasn't 2/3. It was 3/4. This might seem like a tiny mathematical nitpick, but in biology it changed everything. This became known as Kleiber's law. It states that as an animal gets larger, its metabolism doesn't slow down quite as much as the surface law predicted, but it doesn't stay linear either. Every time you double the mass of an animal, its energy needs only go up by about 75%, not 100%. There is an efficiency of scale. Being big makes you more efficient. An elephant is essentially a much more frugal biological machine than a mouse. If we go back to our tragedy with Tusko, we see the fatal error. If the researchers had used Kleiber's law instead of linear math, they would have realized that Tusko didn't need a dose 1,000 times larger than a cat. He only needed about 50 milligrams. By giving him 300, They gave him a massive, lethal overdose because they failed to account for the efficiency of his size. But Kleiber's law was only the beginning of the mystery. Once biologists started looking, they realized that this quarter-power pattern was everywhere. It wasn't just metabolism, it was brain size. It was the thickness of tree trunks. It was the time it takes for blood to circulate. And most surprisingly, it was the number of times a heart beats in a lifetime. If you take an African elephant, its heart beats slowly, about 30 times per minute. It lives a long, majestic life, often reaching 70 or 80 years. If you take an Etruscan shrew, the smallest mammal on Earth, its heart is a frantic blur, beating 1,200 times per minute. It lives fast and dies young, usually in less than 2 years. But here is the mind-blowing part. If you take that elephant's heart rate and multiply it by its lifespan, and then you take that tiny shrew's heart rate and multiply it by its lifespan, you get almost exactly the same number. 1 billion. Nature gives almost every mammal on this planet a budget of 1 billion heartbeats. You can spend them fast, like a shrew, and be done in a year. Or you can spend them slowly, like an elephant, and stretch them over a century. But once that billionth tick happens, the motor stops. Except for us. The human glitch and the fourth dimension. If you were a betting person looking at the history of life on Earth, you wouldn't bet on humans. We are, by all biological accounts, a massive glitch in the system. If you take a primate of our mass, about 70 to 80 kilograms, and plug it into the math of the 1 billion heartbeat law, we should be dead by the age of 25 or 30. For most of human history, that's exactly what happened. 3 centuries ago, before the dawn of modern medicine and sanitation, the average human life was a frantic sprint. We were much closer to that standard billion-beat limit. But then, something unprecedented happened. We didn't wait for evolution to change our bodies. We used our minds to change our environment. Through the discovery of germ theory, the invention of antibiotics, and the simple act of purifying our water, we didn't just extend our lives, we doubled them. Today, the average human doesn't stop at 1 billion beats. We push through 2 billion. We are cruising toward 3 billion. In biological terms, we are living with the lifespan of a creature twice our size. We are effectively living extra lives that nature never intended for us to have. But why is the limit there in the first place? Why can't a mouse just decide to live for 70 years? To find the answer, we have to look inside our own bodies, not at the organs, but at the plumbing.
In the late 1990s, a team of 3 scientists, Geoffrey West, a high-energy physicist, and 2 biologists, Jim Brown and Brian Enquist, decided to solve the mystery of why everything in nature seems to scale by the number 4. They realized that whether you are a tree, a whale, or a human, you face the same engineering problem. How do you get nutrients and oxygen to every single one of your trillions of cells as efficiently as possible? Think about it. Every cell in your body needs to be serviced. If a cell is too far from a blood vessel, it dies. But if you filled your body with nothing but blood vessels, there'd be no room for anything else. Evolution had to find a space-filling solution, and the solution it found is one of the most beautiful concepts in mathematics: the fractal. A fractal is a pattern that repeats itself at every scale. Think of a tree. The trunk splits into branches, which split into smaller branches, which split into twigs. If you look at a photo of a single twig, it looks remarkably like a tiny version of the whole tree. Your circulatory system is exactly the same. Your aorta branches into arteries, then arterioles, and finally into capillaries. West, Brown, and Enquist realized that these fractal networks aren't just pretty shapes. They are the ultimate efficiency hack. But they come with a weird mathematical consequence. In standard geometry, we live in a 3-dimensional world. Volume scales with the cube of length. If you double the size of a cube, its volume increases by 8. But when you create a fractal network that is so dense it reaches every single point in a three-dimensional space, that network effectively adds a whole new dimension to the organism. Biologically speaking, even though you look three-dimensional, your internal distribution system makes you function as if you are four-dimensional. This is why the quarter-power scaling laws exist. In a 3D world, we'd expect everything to scale by thirds. But in our fractal plus one reality, nature scales by fourths. This fractal architecture is why a whale is so much more efficient than a mouse. In a mouse, the plumbing is short and works at high pressure. It's violent. It's exhausting. It creates massive amounts of metabolic damage. Think of it as biological wear and tear. Every time that tiny heart hammers at 1,200 beats per minute, it's like redlining a sports car engine. The friction of the blood, the oxidative stress on the cells, it all adds up.
The mouse burns through its billion-beat budget in a flash. But as you get larger, the fractal network gets deeper and more efficient. The blood slows down, the pressure stabilizes. An elephant's heart beats with a slow, majestic thud, because its massive fractal network allows it to distribute energy with far less friction per unit of mass. This brings us to a startling realization. Death isn't an accident. It's a mathematical certainty built into the way we are plumbed. Your lifespan is essentially the time it takes for your metabolic engine to clog up or wear out based on the efficiency of your size. But if scaling is so perfect, why do cities follow the same rules? This is where Geoffrey West's research took a turn into the truly bizarre. He discovered that if you know the population of a city, you can predict its heartbeat too. If you double the size of a city, you don't need double the gas stations or double the length of electrical cables. You only need about 85% more. Cities, like animals, have economies of scale. They get more efficient as they get bigger. But there's a dark side. Unlike animals, which slow down as they grow, cities actually speed up. In larger cities, pedestrians literally walk faster. Crime scales superlinearly. Disease spreads faster. We have built superorganisms out of concrete and steel that follow the same fractal laws as our own blood vessels. And just like us, they are racing against their own internal clocks. But there is one final piece of the puzzle. If humans hacked the heartbeat law to live 3 times longer, can we do it again? Or are we reaching the ultimate wall that even math won't let us climb? The ultimate wall and the heartbeat of civilization. If humans have managed to hack the system and push our budget from 1 billion to 3 billion beats, a natural question arises. Why stop there? If antibiotics and clean water gave us an extra 2 billion, why can't nanotechnology or genetic engineering give us 10 billion? Why can't we live for 500 or 1,000 years? To answer that, we have to look at the dark side of the fractal math we discussed earlier. The same networks that deliver life-sustaining nutrients also deliver the seeds of our destruction. Every time your heart pumps blood through those branching vessels, it's not just a delivery, it's a collision. At the microscopic level, the flow of blood creates friction, turbulence, and oxidative stress. Think of it like water rushing through a pipe. Over time, that water will inevitably erode the metal, no matter how well built the system is. In biology, this is the metabolic damage theory. Your lifespan is effectively the time it takes for your internal plumbing to sustain enough structural damage that the system can no longer repair itself. While we have become masters at preventing accidental deaths, like infections or predators, we haven't yet figured out how to stop the fundamental physics of wear and tear built into our four-dimensional geometry. Science has stretched our timeline, but it hasn't removed the clock. There is a mathematical wall where the energy required to repair the damage exceeds the energy the system can produce. That is the point where the motor finally stops. But there is a second clock we are all racing against, and this one isn't inside your chest. It's the city you live in.
As we mentioned, Geoffrey West discovered that cities are also biological systems, just on a much larger scale. They are made of the same space-filling fractal networks. The roads are our arteries, the electrical cables are our nerves, and the water pipes are our veins. And just like animals, cities get more efficient as they grow. A city of 10 million people is significantly more energy efficient per person than a town of 10,000. However, cities have a terrifying property that animals do not. In the animal kingdom, as creatures get larger, life slows down. A blue whale's life is a slow, rhythmic dance. But in the urban organism, as the population grows, everything speeds up. Researchers have literally measured the walking speed of pedestrians in hundreds of cities across the globe. The math is undeniable. The more people there are in a city, the faster the average person walks. And it's not just walking. In larger cities, bank transactions are faster. The frequency of social interactions is higher. Innovation, measured by patent filings, scales superlinearly, meaning big cities produce ideas much faster than small ones. But there is a price for this speed. Crime, disease, and social stress also scale superlinearly. For every doubling of a city's size, you get a 115% increase in both the good, wages and wealth, and the bad, crime and pollution. We have built environments that are constantly demanding us to beat our hearts faster, think faster, and move faster just to keep up with the rhythm of the collective. This is the Great Acceleration. In 1825, the writer Wolfgang von Goethe complained that life was becoming ultra, that wealth and rapidity were all the world admired. He felt the world was moving too fast 200 years ago. Imagine what he would think of our digital age today. We are living in a super-biological reality where the heartbeat of our civilization is accelerating exponentially, even while our biological hearts are still tethered to that ancient 1 billion tick rule. So, what is the bottom line? What does the 1 billion heartbeat law actually teach us about our lives in 2026? First, it teaches us that life is not linear. We often think that if we work twice as hard, we will get twice the result. But nature shows us that scaling is sublinear. Success, health, and growth all follow laws of diminishing returns and hidden efficiencies. Understanding the quarter power rule allows you to see the hidden constraints of reality. It tells you that there are no deals in nature that don't come with a cost. Second, it reminds us that frugality is the secret of the giants. An elephant lives 70 years not because it is stronger than a shrew, but because its system is more efficient. It doesn't waste its energy. It spends its billion beats with a majestic, calculated patience. In a world and a city that is constantly screaming at you to run faster, perhaps the most radical thing you can do is learn to slow down your metabolic rate. To live with the rhythm of an elephant in a city that moves like a hummingbird. Finally, it puts our mortality into a beautiful mathematical perspective. We are the only creatures on this planet that have been given extra time by the power of our own intelligence. We have cheated the ancient code. We are living 2 full lives that nature never intended for us to have. When you realize that your heart is a finite motor with a preset budget, time stops being an abstract concept. It becomes a physical currency. Every tick is a coin you spend. You can spend those coins on stress, on anger, or on the frantic noise of the city. Or you can recognize that you are a biological miracle, a 3-dimensional being functioning in a 4-dimensional fractal reality, living out a glitch in the matrix that gives you 3 billion chances to feel, to love, and to discover the secrets of the universe. Nature gave every mammal a billion heartbeats. Science gave you 3 billion. How will you spend yours?